Hello, so in this video I want to share a circuit with you that is a common emitter, and we're gonna do the entire simulation in Cooks in Ubuntu, as you can see. Okay, so in this interface, in the main interface, you can go to the components panel, and there are lumped elements and as well as nonlinear components. There are also libraries. You can take a BJT from transistors, like one of these. But as you can see, uh, the datasheet has been already done. So, for example, the BF is right here, the beta, and also the noise figure and other stuff, and also the IS, which is uh, used for calculating IB, and then from IB, or the current of the base, you can get the current of collector. Okay, so I'm gonna go back to the components because I want to take an ideal NPN BJT. Okay, so I put it over here, and okay, let's use it. Then I'm gonna head to the lump components. At first, I'm gonna right click so to rotate any element I want. And as you can see, at first I'm gonna take care of the base of the bias of the base. I'm gonna take my wires from up there and do the wiring of the base bias, and click, click, click. Okay, that was a little bit too much, maybe, but I can take it and do that. I can take a ground from up there, and I'm gonna bring it down like this, and then a wire as well as a wire. And now I'm gonna say, okay, I want 0.8 volts or 0.7 volts at the base of the BJT. So I'm gonna say, hey, like this is 10 kilo ohms, and then I'm gonna make sure to press an enter on that, and then I'm gonna say 7 kilo ohms for the lower resistor, and then having taken care of the DC part, I'm gonna bring in the AC part later. But I'm gonna, from the sources panel, I'm gonna get or take DC voltage, and then I'm gonna say, hey, 10 volts is enough for now, and then I'm gonna put another resistor up there in the collector, wire it up, and once I'm done with this, I'm gonna head over to the simulation panel and take a DC simulations to see what the working point of my BJT is right now. Okay, so I'm gonna say calculate the DC bias, and at first it prompts me to save my project simulation, and then I'm gonna say simulate again. After this, I see that I got 4 volts over here, and it means that it is on, and once it is on, then this is 0 and this is 10 volts. Okay, that is not good. Why? Because this 50 ohm is not that big. I'm gonna give it 10 kilos and see if this actually really turns on. Okay, so right now it's still it is turned on, but the IC is not flowing down. Okay, I'm gonna make this 10 to 1000, and there's still a problem. So I would, at this place, I would change my BJT with a real BJT. So I'm gonna head over to the transistors and gonna take one of these 2N2222A, and then I'm gonna take a look at the data sheet, and it says beta F is 205 and the reverse beta is 4 and CJE. So this is obviously not a perfect or ideal BJT, because there's a CJE, CJC, and a CJS, which is 0. So the CJE and the CJC are the capacitance for the base collector and the base emitter, and these are the factors that determine the matrices, S matrix of our lumped element when it is used in a non-lumped manner. So I'm gonna for now replace this back and see what the deal is. Why are you not turning yourself on? Turn on again, please. Okay. Now that's interesting. Something's off. 7 kilo. Okay, this is not good. The bias is not correct. If this is, yes, the bias might be correct actually. I can make this 1 kilo and then F8, use F8. Okay, now this is better. And after this, I can head over here and say 100 kilos, F8. This is still not working. F8. That's not cool. I can use this one, for example, and then bring this over there and say, hey, VAF, this is good. The forward early voltage, the reverse early voltage, and the IS, this is good. The beta F, this is as well good. I can turn this into 0 and then head down there. And turn this into 0 as well. And after this, I'm gonna get an F8, and I can see that the working point has changed this time, and that is good. It has changed into a reasonable voltage that I like to see. Okay, so I'm gonna say this and then this. Okay, 123 millivolts and a reasonable voltage that shows the VBE, which is right here probably, that tells us at what voltage the BJT goes on. So the base emitter junction built-in potential is 7.75 volts. Okay, so I'm gonna change this to, let's just go over to 3 and be safe. And I'm gonna use F8. Okay, this is a fixed voltage. This just didn't change. So F8 didn't change that much either. F8. Okay. I don't know what is going on. Okay, now this is on, turned on completely. And as we can see, once this is turned on, then if there is a 0 volt here, we have a VCE over there, up there. And this is still not good because this BJT finds itself not in a totally on position or a region, because it's like triode. The base collector junction must be in reverse bias so that the electrons that are emitted from the emitter get pushed to the collector so the collector could collect them. So right now this is a problem that I'm facing for the working point of the okay, now things have changed. Now that changed again. F8. Okay, now this is not good. Why is it not good? Because the base is AP and then the collector is an N. This is a forward bias and this is not good. So I'm gonna head over back to the ideal components, or just stay here and try it with another component. Right here, I use F8. Okay. This is still not good. No, this is not good. I'm gonna use another ideal component. Okay, now this is good. This is not bad, but this doesn't look that good. Three volts, 10 volts. This means that this hasn't turned on yet. And the problem is that this is not working. And why is it not working? I don't know. I'm gonna head back to another BJT and say, okay, this. Okay, now this is good. Now this is really good, and I'm gonna turn this into something even better. Okay, now this is perfect. I'm using this component which has an IS of, excuse me, oh, wait a second. Okay, which has this IS and one noise figure, forward emission coefficient, and NE, which is a leakage and base emitter leakage, the NP junction. This is the NE that is used in the IS formula, and it is the mobility of the coefficient of the mobility of the electron emission of the PN junction at the base emitter. And the BF or the beta F is the forward beta, which is IC equals beta IB, and IC or the current of the collector is IS, which is here given here, saturation current, times the exponent of VJE over V thermal. And the V thermal, I don't know if it's given over here, but it is at 26 Celsius, the temperature. And then the V thermal is probably, I don't know where that is. It's probably this one, but it's 0. It should be around 25 millivolts or 26. Okay, that number is only given for the temperature. And then now I have a good amount of collector voltage, which puts this junction, this PN junction between base collector in deep reverse. Okay, so when it is in deep reverse, it means that it's like saturating the PN junction into reverse and just shooting incoming electrons from emitter over to collector. And so after taking care of the bias and the working point of the NPN transistor, I can head over to the AC part of everything, and I could put a capacitance. A capacitor comes over here. I can also rewire everything like this, very easy. And then I can head over to the sources and rewire everything like this again. And okay, that's nice, very elegant. I can give it 1 volts or 10 volts of AC, but doesn't really make a difference. I'm gonna turn this into a megahertz, and then I'm gonna just take a look at the collector voltage as the Q, and then an input voltage over here at the base, and then I'm going to take care of the P. I'm going to let it be picofarads for now for you to see how that changes the frequency response in the Bode plots. So over here I head over to the simulations panel and go to transient simulation, and let's just get an output of everything. Let's see. Okay, in Cooks, this is how you can see the stuff that you are plotting or testing. Okay, now this doesn't look good. Okay, what should I be changing. Okay, just remember I gave it a 1 megahertz, so I can make this a 1 microsecond and just give it a 20 points. Okay, so this looks sinusoidal. Yes, that's good. That's a good start. And I can print like 5 cycles, and I want 100 numbers. Okay, of simulations, and these are probably working with some point approximations, some Newton-Raphson modelings of a circuit, because these are all nonlinear functions. They use Newton-Raphson behind the scene of these sorts of software. Okay, so that is too many cycles. I can make that 3, which is enough for me for now. I can turn this over to 200 and take a look at it again. That is beautiful. I can also bring in the output voltage, and you can see that it is not that neat for now. We're gonna see why in a couple of minutes. But this is the A, and I want to see only the Q, or the output, which looks like this. Okay, so we're gonna head over here. I'm gonna meddle with the picofarad and make it turn it into a microfarad. And the output of it doesn't look good. I just forgot. This is the output. Okay, this actually doesn't look that bad. Yeah, it actually. We will see why it doesn't look that bad. I will. Okay, for now, let me filter out the DC part of this. Okay, so this is still not complete, of course, and okay, I'm gonna turn it into a nano, and then bring this down there, rewire everything, and put a new label up there, and I'm gonna call it O. Okay, so O, and I can keep it to 1 nanofarads or a microfarad. And after this, I'm gonna take a simulation. Okay, so the 1 volt AC is probably too much for it. I'm gonna turn it into 1 millivolts, because usually in electronic circuits we work with millivolts and milliamps. So this is how the output looks. It's a sinusoidal. I can get rid of the input, and you can see that it's a purely sinusoidal. That looks great. And because I turned the volume of the input down, so the amplitude is down, so that this output of the circuit doesn't head or shoot to saturation. Okay, so I can also right now work on the Bode plot as well, but I wanted to show you something before we head over to the Bode plot. So this is around 2.74, 0.4 volts here down on the down cycle, and then 0.45, no, 0.045, yeah, 0.045 volts, which is like 45 millivolts. It has turned 1 millivolts to 45 millivolts, so that is quite a gain. Not that much, but still good. And then I'm gonna head over here and turn this transient into an AC simulation which just sweeps some frequencies in logarithms. Okay, so I'm gonna say till 10 megahertz and 19 numbers. Okay, this is a check DC nonlinearity. DC action is required. Okay, I'm also gonna put a DC simulation over there and then head over to the charts. Okay, I'm gonna turn this into a logarithmic plot because I of course want to see the AC frequency sweep of the output, and this is how it looks. Okay, so I can also head back there and say, hey, I want like 50 points instead of 19 so that everything looks neat. Okay, so as we can see, our plot has a 0 and a pole. Why? Because it has a 20 dB plus in the slope over here. So the roll off, you could say, or 3 dB, like is around here, and then the 3 dB is up there. So it's like 1 0 is around here, like between 500 hertz to 1 kilohertz, and another one is like right below 10 kilohertz. And so I can also show you what these capacitors do. For example, if we got a bigger capacitor, then that means like I got a negative J over omega C, which translates into a lower 0. So I expect that this 0 comes over to the left, and if I meddle with this one and, for example, turn this into a nanofarad, then I expect that this moves further to the rear. So let's go back and get a simulation, and as we can see, I speculated falsely with the 0. Okay, so yeah, the 0 also headed more to the rear. Okay, so let me think for a second. Yeah, 1J, negative J over omega C means a bigger C. Wait. Okay, this doesn't look good. Okay, this is probably not changing anything. That is suspect for. I don't know why. So let me check it out. Okay, the 0 doesn't change anything, but this is a 0. I don't know why. 1 microfarads. I'm gonna turn this into 10. Okay, apparently it only changes itself with the pole. I don't know why. It changes slightly in it. No, it doesn't change anything. Okay, So let me change the 0 that the base collector capacitor puts in. So there is also a base collector 0 bias. I can turn this into, instead of 20 picofarads, I can turn this into like 20 microfarads. And simulate. Okay, so I can see another 0 in a pole. So the Miller effect, if you see this, okay, oops, this is from overlay. Okay, so this is the base, and this is the CJC, which goes to the collector with the early effect, and there is the R pi, there is this one, and this is the emitter, and this is the collector. So this is the CJE, and this is the CJC. So when we change this, this becomes a CJC, which comes over here, and to the E CJC1, and this just turns into 2 capacitors with the Miller effect, and this probably becomes like 1 plus GM 1 plus over GMRD or GMRC times CJC. So we have basically a 0 and a pole, and this is not emitter, this is collector. Okay, and no, this is actually emitter. Wait, yeah, this is, so emitter is right now to the ground, hooked to the ground. So as 0 and a pole shows itself in there. This is why we see a 40 dB plus, which is an excessive 0, and then a pole, probably this is 40 dB, I guess, and then 2 poles, and another 0, and another pole. And I come over here and change the CJC again. I change this back to, I can say, hey man, I want a very, very tiny 0 so that it doesn't change my Bode plot at all. So that my Bode plot doesn't change because of the CJC and the CJE. So I come over here, down there, I change the CJC right now. I can as well change in the CJE and say, hey, you can move further to the rear, like to the beginning, like, because this is a 0 as well. Of course, it doesn't change anything that much, which is good. And this is looking, okay, this is not changing. This is a little bit problematic. I can make another video later and change these things, yes. Yeah, but this is it for now. I can also show you another another transient, because the transients with this, they look good. I forgot to take a picture of the last one, but if I remember correctly, like the output frequency. Oh, now I see what the problem was. Okay. Yeah, the plot the plot wasn't changing while I was changing this. The plot wasn't changing. I can change this. Okay, then you can see that the 0 is changing, and I can also change this. So the problem is that the pole is not working. Wait. Okay. No, that's not good. Okay. So over here is 0, and this is logarithmic. It's not. Okay, now that's good. Now I change that into these values. Okay, so as you can see, I turned this higher, and now this worked. And if I turn this lower, then the 0 should be moving. So 1 over omega c with a lower c, then I got a bigger 0, and then this moves further to the right. Yes. And then if I put this to u, as it moves further to the left of 0, and I can of course meddle with the pole, and the pole changes slightly. So okay, so I want to show you now for example, the 10 kilohertz or 100 kilohertz transient. So the transient, if I change this down over to transient, okay, linear, that's good, 150, and I want a 10 kilohertz, 100 kilohertz, that's well above this 1 megahertz is over here. So I'm gonna see probably no phase shift, or let's see. Okay, now I change this to A and Q, QET. Okay. Okay, that's good now. U and QET, AVT. Okay, so now you can see that there's a 180-degree phase shift between the input and the output. So it is 10 megahertz, which is well above the pole and 0. And there's a slight difference in phase. There's a slight shift in phase, and if I turn this 1 megahertz into 1 kilohertz or even less, then for example 100 hertz, then this becomes a huge phase shift. Then this becomes 100 milliseconds. Okay, so now you can see that there is a huge mismatch. Like, okay, the frequency is too low. I can maybe change this into 1 kilohertz and then take a look. Okay, so there is a huge phase shift and the output doesn't look symmetric somehow, and this is how it should be actually. Like, it's below uh, it's below 100 kilohertz as that was in the Bode plot, and so okay, as you can see, there is a mismatch between the two. There's not a 180-degree phase shift anymore. The input, which is the A, has moved further to the left with respect to the Q, which is the output, and the output has probably shrunk. Yeah, it's not 45 anymore. It has shrunk down. It's not 45 millivolts anymore. This is how it should be. So I thank you for accompanying me throughout this video, and I will get back soon with another video of some other lumped elements simulations. Okay, so I wanted to correct something. Here it has only one zero, one pole, one zero, and another pole. During the video I said that this is 2 zeros because the slope was too steep. Thank you.